Everything you can see, touch, and measure, all of it came from somewhere. The stars, the planets, the air, even you, all of it started from a single event. That event is called the Big Bang, and it is not what most people imagine. It was not an explosion in space. It was the beginning of space itself. It was also the beginning of time. Before the Big Bang, there was no before. In this video, we are going to walk through the entire story, step by step, from nothing to now. Before we explain what happened, we need to ask a harder question. What was there before the Big Bang? The answer is, we genuinely do not know. And that is okay. Science is comfortable with honest unknowns. What we do know is that our current laws of physics break down at that point. They simply stop working. It is like asking what is south of the South Pole. The question itself stops making sense. So when we say, the beginning, we mean the earliest point our physics can describe. Everything we are about to tell you starts from that dot, from t equals 0. At t equals 0, everything that exists was squeezed into an unimaginably tiny, hot, dense point. Physicists call this a singularity. It is not a place inside space. It is space itself, collapsed to a point. Temperature at this point was so high that no atoms could exist. No particles could exist. Nothing we recognize could exist. All four fundamental forces of nature were merged into one single unified force. Think of it like one type of light passing through a prism and splitting into many colors. At the singularity, it was all one beam. We cannot perfectly describe what this singularity was. But we know the universe expanded from it. Now the story really begins. The universe starts expanding, and it does so incredibly fast. In the first tiny fraction of a second, the universe went through a phase called inflation. During inflation, space itself expanded faster than the speed of light. That is allowed. Space has no speed limit. In less than a trillionth of a second, the universe grew from smaller than an atom to the size of a grapefruit. Why did this happen? The leading theory is that a kind of energy called inflaton energy drove this expansion. After inflation ended, the universe kept expanding, but much more slowly. And it has been expanding ever since. As the universe expanded, it cooled. This is the same reason a spray can feel cold. Expanding gas loses heat. In the earliest moments, the universe was a hot soup of pure energy. No particles yet. Then, as cooling began, that energy started converting into matter. Energy became particles. But here is the interesting part. For every particle of matter, an equal particle of antimatter was also created. When matter and antimatter meet, they annihilate. They destroy each other and release pure energy. If matter and antimatter had been created in exactly equal amounts, they would have destroyed each other completely. But somehow, for every billion antimatter particles, there were 1,000,000,001 matter particles. That tiny imbalance, just one extra particle per billion, is the reason anything exists today. This imbalance between matter and antimatter is one of the biggest unsolved mysteries in physics. Physicists call this the matter-antimatter asymmetry problem. We know it happened. We do not fully know why. One clue is that the laws of physics treat matter and antimatter almost, but not perfectly, the same. That tiny difference is called CP violation, and it is an active area of research today. For our story, the important thing is this: matter won. And from that leftover matter, everything was built. Now we are about 1 second after the Big Bang. The universe is cooling rapidly. The first stable particles to form were quarks. Quarks are the building blocks of everything inside an atom. 3 quarks bind together to form a proton. 3 quarks in a different combination form a neutron. Protons and neutrons are the particles that make up the nucleus, the core, of every atom. Electrons also formed around this time. Electrons are much smaller and carry a negative charge. At this point, the universe was still too hot for electrons to attach to nuclei. They just flew around freely. The universe was like a thick fog. Light could not travel far because particles kept bouncing it around. About 3 minutes after the Big Bang, protons and neutrons began sticking together. This process is called Big Bang Nucleosynthesis. Nuclei are the cores of atoms, the protons and neutrons packed together. The simplest nucleus is just one proton. That is the nucleus of hydrogen, the most common element in the universe. The next nucleus is 2 protons and 2 neutrons. That is helium. It formed abundantly in the early universe. A small amount of lithium, 3 protons, also formed. That was it. Nothing heavier could form yet. Why? Because the universe was expanding and cooling too fast. Nuclei did not have time to fuse into heavier elements. This means that for the first few 100 million years, the universe contained only hydrogen, helium, and a little lithium. After nucleosynthesis, the universe entered a long, quiet period. No stars. No light. Just particles and gas drifting apart. This era lasted about 380,000 years. During this time, the universe was still opaque. Light could not travel freely. Then, at 380,000 years after the Big Bang, something important happened. The universe cooled enough for electrons to slow down. When electrons slowed enough, they were captured by nuclei. Protons and electrons combined to form complete atoms. This moment is called recombination, though really it was the first time they ever combined. Once atoms formed, the universe became transparent. Light could now travel in straight lines. That light, the first light that could ever travel freely, is still traveling today. We call it the cosmic microwave background. The cosmic microwave background, or CMB, is one of the most important discoveries in all of science. It is a faint glow of microwave radiation that fills the entire universe uniformly in every direction. In 1965, 2 scientists accidentally discovered it, Arno Penzias and Robert Wilson, while testing a radio antenna. They kept hearing a faint static signal from every direction. No matter where they pointed their antenna, the signal was there. That signal was the afterglow of the Big Bang itself. The first light, stretched and cooled over 13.8 billion years. Today, the CMB temperature is just 2.7 degrees above absolute zero, almost as cold as space can get. The CMB is not perfectly smooth. It has tiny temperature variations, hot spots and cold spots. Those tiny variations are clues. They show where matter was slightly denser, and those dense spots became stars and galaxies. After recombination, the universe was mostly uniform, but not perfectly. Some regions had slightly more matter. Gravity is attracted to mass. Where there is more mass, gravity pulls more matter in. Over millions of years, gravity pulled hydrogen and helium gas into giant clouds called nebulae. As these clouds collapsed inward, they became denser and hotter at the center. When the core reached about 10 million degrees, something remarkable happened. Nuclear fusion ignited. A star was born. The first stars in the universe turned on about 100 to 200 million years after the Big Bang. A star is basically a giant balancing act between two forces: gravity trying to collapse it, and fusion pushing outward. Inside the core, hydrogen nuclei are slammed together with enormous force. They fuse into helium. When they fuse, a tiny amount of mass is converted to a huge amount of energy. That is Einstein's E equals mc squared. That energy radiates outward as light and heat. It is what makes the sun shine. Stars are also element factories. As they burn, they fuse hydrogen into helium, then helium into carbon, then into oxygen and more. This is called stellar nucleosynthesis, the creation of elements inside stars. All the carbon in your body was made in a star. Stars do not last forever. When a star runs out of hydrogen fuel, the balance breaks. For smaller stars like our Sun, the outer layers puff outward into a red giant. Then they slowly release gas into space. But for massive stars, those 8 times or more the mass of our Sun, the ending is explosive. When a massive star collapses, the core bounces and triggers a catastrophic explosion called a supernova. A supernova releases more energy in seconds than our Sun will release in its entire lifetime. The explosion blasts all the elements the star created, carbon, oxygen, iron, out into space. Those scattered elements become the raw material for new stars, new planets, and eventually, life. Here is something that might surprise you. All the stars, planets, gas, and dust you just heard about, that is only 5% of the universe. About 27% of the universe is something we call dark matter. We cannot see it, but we can detect its gravity. We know dark matter exists because galaxies spin faster than they should if only visible matter were there. The remaining 68% is even stranger. It is called dark energy, and it is causing the universe to expand faster over time. Dark energy is not a particle or a force we understand. It seems to be a property of space itself. Both dark matter and dark energy are among the biggest unsolved mysteries in physics today. Back to the story. After the first stars turned on, gravity continued to gather matter across enormous scales. Millions and billions of stars clustered together under gravity, forming the first galaxies. The first galaxies formed about 400 million years after the Big Bang. They were smaller and more irregular than today's. Galaxies collide and merge with each other. Our own Milky Way galaxy formed this way over billions of years. Our Milky Way contains roughly 200 to 400 billion stars. And there are roughly 2 trillion galaxies in the observable universe. All of these structures, every galaxy, every star, grew from those tiny temperature variations in the early CMB. About 4.6 billion years ago, inside our own galaxy, a cloud of gas and dust began to collapse. This cloud was made of hydrogen, helium, and heavier elements scattered by ancient supernovas. As the cloud collapsed, it began to spin. Conservation of angular momentum made it spin faster and faster. The spinning cloud flattened into a disk. The center grew hotter. Eventually, fusion ignited, and our sun was born. In the disk surrounding the sun, dust and rock began to stick together, a process called accretion. Over millions of years, these growing clumps swept up more material, eventually forming the planets. Earth formed about 4.5 billion years ago. Early Earth was covered in molten rock. There was no life, no water, no atmosphere yet. Over hundreds of millions of years, Earth cooled. Water vapor condensed into oceans. An atmosphere formed. About 3.8 billion years ago, the first signs of life appeared in the oceans. Simple single-celled organisms emerged. These first cells were made of atoms that came from stars. Carbon, oxygen, nitrogen, all forged in stellar furnaces. Over billions of years, life evolved from single cells to complex creatures, and eventually to humans. Every atom in your body has a history that stretches back to the Big Bang. Now let us zoom back out. The universe has been expanding ever since the Big Bang. But is it slowing down? In 1998, 2 teams of astronomers made a shocking discovery. The expansion is actually speeding up. This discovery won the Nobel Prize and revealed that something, dark energy, is pushing space apart at an accelerating rate. This means that faraway galaxies are moving away from us faster than the speed of light. Not because they are moving through space at that speed, but because the space between us is stretching. There is a boundary, called the observer. At this point you might ask, how do scientists actually know any of this? It all sounds very abstract. The first major piece of evidence is the CMB, that afterglow of the Big Bang we discussed. It exactly matches predictions. The second piece of evidence is the ratio of hydrogen to helium in the universe. It perfectly matches Big Bang nucleosynthesis calculations. The third is the expansion of the universe itself, discovered by Edwin Hubble in 1929 by observing that all galaxies are moving away from us. Hubble's discovery implied that if you run time backward, all galaxies converge to a single point, a Big Bang. Fourth, Particle accelerators like the Large Hadron Collider recreate extreme early universe conditions and confirm our models. All 4 lines of evidence point to the same conclusion. The Big Bang happened, and our model of it is very well supported. Let us clear up some common misconceptions about the Big Bang. First, it was not an explosion in space. Second, the Big Bang did not happen at a specific location in space. It happened everywhere at once. Third, the Big Bang is not a theory about what was there before. It only describes what happened after t equals 0. Fourth, saying it is just a theory misunderstands what a scientific theory is. A theory is an explanation supported by massive evidence. The Big Bang theory does not mean someone guessed it. It means it has been tested repeatedly and survived every test. We have come a long way. But what happens next? What is the future of the universe? The universe will continue expanding. Stars will continue forming for the next trillion years or so. After that, the gas needed to make new stars will run out. The last stars will burn out, one by one. Over unimaginably long timescales, even black holes will slowly evaporate through a process called Hawking radiation. Eventually, in what scientists call the heat death of the universe, everything will reach the same temperature. That is the most likely long-term fate. A cold, dark, uniform universe, far in the future. But we are nowhere near that fate. Right now, the universe is still young, still active, still full of stars being born. Let us bring the whole story together. Everything begins at t equals 0, the singularity. The universe inflates and cools. Energy converts to particles. Matter barely wins over antimatter. Protons and neutrons form. Nucleosynthesis builds hydrogen and helium. The universe is opaque. At 380,000 years, recombination clears the fog. The CMB is released. The universe becomes transparent. Gravity pulls matter into clouds. The first stars ignite. The first galaxies form. Stars forge heavy elements and scatter them via supernovas. Our Sun and Earth formed 4.6 billion years ago. Life appears, evolves, and eventually, intelligent beings look up and ask how it all began. You might wonder, why does any of this matter? What does the Big Bang have to do with everyday life? Every atom in your body was forged inside a star. You are not separate from the universe. You are part of it. Understanding the Big Bang helps us understand why anything exists, why there is something instead of nothing. It also gives us humility. Our entire planet is one tiny dot in a universe of 2 trillion galaxies. And it gives us wonder. Because somehow, from a single point smaller than an atom, all of this complexity arose. That is what makes physics beautiful. The universe plays by rules, and we figured out enough of those rules to trace our own origin. The Big Bang model is powerful, but it is not complete. There are real gaps that scientists are actively working on. We still do not know what dark matter is made of. It makes up 27% of the universe, and we have never directly detected it. We still do not understand dark energy, the 68% that is causing the universe to accelerate. We still do not have a complete theory that unifies quantum physics with gravity, the two pillars of modern physics. And we still do not know what happened at or before t equals 0. The singularity remains beyond our current physics. These gaps are not failures. They are the next frontier. Every unsolved question is an invitation for the next generation of scientists. Let us end where we began. 13.8 billion years ago, something began from nothing, or from something we cannot describe. From that point, energy became matter. Matter became atoms. Atoms became stars. Stars became galaxies. Galaxies built planets. Planets made life. Life made you. And you, a collection of stardust, found a way to look back at the beginning and understand it. That is the Big Bang. Not just a scientific theory. It is the story of everything, including you. Thanks for watching Cosmic IQ. If you found this helpful, share it with someone who has ever looked at the night sky and wondered where it all came from.